Good evening, everybody. Let's wait for a few minutes. So the first problem is we need to find intrinsic resistivity. The intrinsic resistivity of germanium at 300 Kelvin is given as 0.47 ohm meter, and the electron mobility and also the hole mobility is given at the same temperature. Now we need to calculate number one, the density of electrons in that intrinsic germanium, and after that we need to calculate the dip velocity for both the electrons and holes, given the electric field is 10 to the power 4 volt per meter. So again, same formula that we used in the last session will be applied. So yeah, try to solve and write the answers in chat box. The first answer is correct. This is in per meter cube unit. 2.30 into 10 to the power 19. Right. 1900 would be drift velocity for holes. So any other person, I mean, are these answer matching? These are correct answers. Okay, so let me solve it. So the formula for conductivity is given as n mu, n mu n. N is the electron density plus again so the charge of holes are also E, and then P mu P. Now this is electron density. Now for an intrinsic material, the electron density equal to hole density. This is due to intrinsic material. So then it becomes n mu n plus mu p. Now we have given the resistivity. So the resistivity would be 1 by rho, sigma equal to 1 by rho, and this will be equal to E n mu n plus mu p, right? So then we need to find n, which is 1 by rho E mu n plus mu p. Rho is 0.47 into electronic charge. The mobility is given as 0.39 and 0.19. So if we find that all are in SI unit, so this will be around 2.293 into 10 to the power 19 per meter cube. So this is the first answer. Next we need to find drift velocity. So the formula for drift velocity Vd is mobility into electric field. So we have both the variables. So let's say, so Vd for electron, this will be mu E into electric field. So 0.39 into electric field is given as 10 to the power 4 meter per second. So the electron's drift velocity will be 3900 meter per second. Similarly, drift velocity for holes will be mu p into E. So this will be 1900. Okay, sorry, just a second. So the next question, okay, so the next problem is find the conductivity of intrinsic germanium at 300 Kelvin. Given the information that one impurity atom is added in part 10 to the power 7 germanium atom, and also the intrinsic density of electrons in the germanium are given as 2.5 into 10 to the power 13 per semi cube, and then mobility for electron and mobility for holes are also given. So any idea how do I solve this problem? Is this the conductivity? No, conductivity is not. No, conductivity is not 15,200. No. So we have to find the conductivity after adding the impurity, right? And effectively the concentration of impurity is given because one atom is added per 10 to the power 7 germanium atom. Okay, so let me solve it. So if we try to find the intrinsic sigma or the conductivity of the intrinsic germanium, then it will be Ni intrinsic this will be 10 to the power 13 by 10 to the power minus 2 into cube, right? Okay, so we may not do that because everything is in semi-cube. So effectively it will be again in the SI because the semi-cube at here and this will cancel out. So this will be around 0.04 Siemens per meter or ohm inverse meter. So this is the intrinsic conductivity. Now we need to know the number of germanium atom per semi-cube. And this is 4.41 here in the question it is not mentioned, but it is 4.41 into 10 to the power 22. So this is the germanium atom per semi-cube. So and donor impurity is given as one impurity atom per 10 to the power 7 germanium atom. So that means concentration of donors will be 10 to the power 7 amount of less than the actual germanium atoms, right? So this is 4.41 into 10 to the power 22 by 10 to the power 7. So 4.41, not 4. 15. And nothing is mentioned. That means we actually assume that the onward atom have one one extra electron which doesn't uh, take part in the covalent bond with the germanium, right? So then the concentration from this information, one atom of donor contributes to only one electron. So then concentration of electrons will also be the concentration of donors. So all are in semi-Q, right? So this we denote as Nd, concentration of donor electrons. Now there is a law of mass action which says intrinsic concentration of the material is, or the square of that, equal to number of holes or the concentration of holes and the number of uh, or the concentration of donor electrons. So from this expression we can actually find the concentration of holes, Ni square by Nd. Ni square we already know, Ni is given, and Nd we also know this one. So this will be right. Then the concentration of holes will be 1.417 into 10 to the power 11, I guess. Yes, per semi-cube. Then finally we can find out the conductivity of N-type germanium semiconductor. So Nd is 4.41 into mu n. So mu n will be 3800. The answer would be 2.68. Yes, Ionic. This is the answer. So third question. So there are three questions. The potential difference of 10 voltage is applied longitudinally to a rectangular specimen of intrinsic germanium, and the dimensions are given. Now we need to determine electron and hole drift velocity, and then intrinsic conductivity given the carrier density is 2.5 into 10 to the power 19 per meter cube, and finally the total current, not the current density. Okay, so let's we have a sample. So this is length 25 millimeter, and then width is 4 millimeter, and then thickness is 1.5 millimeter. electric field is applied along this direction, longitudinal direction. Okay, so let's try to find out. So anyone, any of these answers? Okay, so let me solve this. So the mobility for these electrons and holes are not explicitly mentioned here, but we actually may pick up from this one or directly here. This is in SI unit. So here we are given voltage equal to 10 volt, right? And this is applied in this direction. So the electric field is V by L. So 10 by 25 into 10 to the power minus 2. So this will be 400 volt per meter. So deep velocity for electron, or let's say N or V electron, is mu n into electric field. So mu n was 0. 38 in SI unit and then 400. So this will be 152 meter per second. Similarly, V for holes P, this will be mu P into E. So this is the first part. In the second part, we need to calculate the conductivity of the intrinsic germanium. Given the carrier density 2.5 into 10 to the power 19. So sigma is electron charge, then intrinsic carrier concentration mu n plus mu p. So this will be 2.24 again, Siemens per meter. Then the last part said what is the total current. So current is current density into the area of cross section. So here the area of cross section is this one, right? Which is a rectangle and whose side are 4 millimeter and 1.5 millimeter. So area of cross section is 4 into 1.5 into 10 to the power minus 3 square meter square, and J equal to sigma into electric field, right? Sigma is conductivity. So total current, this is total current equal to sigma into electric field into the area of cross section. So 2.24 into 400 into 4 into 1.5 10 to the power minus 6. This is in ampere. Finally, the answer will be 5.376 milliampere. So this is the total current. Okay, so next question. Okay, so the question is, in a given n-type silicon material, if donor concentration is 1 atom per 2 into 10 to the power 8 silicon atoms, and then assuming that effective mass of electron is equal to its true mass, that means effective mass m star equal to m e electron, then find the value of temperature at which Fermi level coincides with the edge of conduction band. Okay, and yeah, so this is a discrete information. Given the density of atoms in silicon is 5 into 10 to the power 28. So we need to find the temperature at which Fermi level coincides with the conduction band edge. So usually in the n-type semiconductor, what happens? So valence band. So this is suppose conduction band, and this is valence band. Then somewhere in the middle, the Fermi energy lies. And we need to find the temperature at which the Fermi energy shifts to at this level, edge of the conduction band. Okay. So we need to find the temperature to shift this Fermi energy up. So try to find out, then I'll solve. Okay, so let me solve it. So first we need to find the donor concentration. Donor means n type impurity is there. This is mentioned here. So there will be donor. So the density of atom is 5 into 10 to the power 28 per meter cube, and then the impurity concentration is one atom, sorry, 1 atom per 2 into 10 to the power 8 silicon atoms. So then donor concentration, or donor concentration will be, there are sorry, 5 into 10 to the power 28 atom per meter cube, right? And per 2 into 10 to the power 8 atoms, there is one atom, one impurity atom. So 5 into 10 to the power 8 atom, sorry, 28 atom, it will be 5 into 10 to the power 28 by 2 into 10 to the power 8 per meter cube. This will be concentration of donor atom. So this is 2.5 into 10 to the power 20 per meter cube. Now we need to find the temperature at condition Fermi energy equal to conduction band edge energy here. So this condition actually translates into donor concentration equal to number of electron concentration in the conduction band, and this NC has a formula which is 4.82 into 10 to the power 21. This constant actually comes from some fundamental constant like electric field, Kb, Boltzmann concentration, sorry, constant, etc. And then Mn by Mp 3 by 2, T to the power 3 by 2. T is the temperature in Kelvin. So Nc is already given by this 4.82 into 10 to the power 21, and Mn by Mp 3 by 2 and T to the power 3 by 2. And now Nd is, we already found, right? 2.5 into 10 to the power 20. So we need to find T. And another information is given here, that effective mass of electron is equal to its true mass. And because of this term is equal to 1. So T to the power 3 by 2 will be 2.5 into 10 to the power 20 by 4.82 into 10 to the power 21. And from this we can find T equal to 0.14 Kelvin. So at very low temperature, this Fermi level goes up to the conduction band edge. Okay. So fifth problem. Okay, so the next question is, if the number density of electrons in the conduction band of a semiconductor at a given temperature is 2 into 10 to the power 19 per meter cube. Now we dope the system lightly with donor impurities, and the number density of conduction electrons at the same temperature becomes 4 into 10 to the power 20. So as we know that impurity increases the carrier concentration or the electron concentration. So we need to find the ratio of majority to minority charge carriers concentration. This is a easy problem, so let's try to find out. So anyone solve this? Okay, so let me solve it. So given the carrier concentration of intrinsic semiconductor is 2 into 10 to the power 19 per meter cube, and then in the doped semiconductor it is 4 into 10 to the power 20 per meter cube, right? And so it is doped with donor impurities. So donor impurities means the number of electrons will be greater after the doping. So majority carriers will be electrons, and then obviously minority carriers will be holes. Now again, if we apply law of mass action, which says intrinsic concentration square equal to n into p. So donor concentration and then Hall concentration. So from this we can know Hall concentration Ni square by N, which is this will be 10 to the power 18 per meter cube, right? So this way we got the donor concentration, sorry, Hall concentration. Now we need to find the majority carrier concentration by minority carrier concentration. So that means we need to find N by P. So N was 4 into 10 to the power 20 by P is 10 to the power 18. So this will be 400. So this is the answer. Okay, so next problem. So consider a metal which obeys Sommerfeld model exactly. Now given that EF is the Fermi energy at T equal to 0 Kelvin and RH is its Hall coefficient, which of the following statement is correct? Right, minus 3 by 2. Okay, we'll solve it. So what is Hall coefficient? Hall coefficient is given by 1 by Ne. N is the concentration or density. density of electrons. Now we know that Fermi energy for 3D free electron gas is given by h square by 2 pi into 3 pi square n, sorry, to the power 2/3. So we need to find n proportionality basically. So n is proportional to ef to the power 3 by 2. Then RH is proportional to n inverse. That means RH is proportional to ef to the power minus 3 by 2. Okay. So then C is the correct answer. So next problem. Okay, so So the effective density of states at the conduction band edge of germanium is given 1.04 into 10 to the power 19 per semi-cube at room temperature. Now germanium has a band gap, just optical band gap, of 0.66 electron volt. Now we need to find the intrinsic carrier concentration in centimeter cube of germanium at room temperature. Let me know which of the options are correct. So anyone solve this? Okay, so the intrinsic concentration Ni given as so this is intrinsic concentration, and then Eg is the band gap, and this part NCNV root over NCNV will be the density, effective density of states. So Ni will be Ni will be 1.04. This total term is given as effective density of state. This one 10 to the power 19 exponential of band gap is 0.66 eV. So kVt. Okay, so I missed a 2 here, 2 kVt. And T is 300 Kelvin. So if we calculate this, Ni comes out to be 3 into 10 to the power 13 per semi-cube. This is the answer. Okay, so next problem. So density of states of free electrons moving in a solid with an energy of 1 electron volt is given by 2.15 into 10 to the power 21 EV inverse semi per semi-cube basically. Now the density of states for electrons moving with an energy of 0.4 eV will be what? So this is density of states, okay, not density. That's why unit is also EV inverse semi to the power minus 3. Try to find it out. So anybody? Okay, so let me solve. So density of states for free electrons, right? So for 3D free electron gas, we saw that density of state is proportional to root over of epsilon. So this is for 3D. And if it is 2D, then e to the power 0 doesn't depend on the energy, 2D free electron gas. And if it is 1D, then e to the power minus half 1D. Okay, so we have this 3D free electron gas, and given that E1 equal to 0.1 ev, right? Okay, so this should be 0.1, sorry. So 0.1 ev, then dn1, or the density of states, is given as 2.15 into 10 to the power 21 ev inverse into semi to the power minus 3. And we have also E2 equal to 0.4 ev. Then we need to find dn2 is what value, right? So we can write that dn1 by dn2 equal to root over e1 by root over e2. So this will be 0.1 by 0.4 equal to half. dn2 equal to 2 into dn1, right? So 2 into 2.115 into 10 to the power 21 ev inverse 7 to the power minus 3. So dn2 is 4.3 into 10 to the power 21. So this is the answer. So 4.3 into 10 to the power. So this one. This is also reasonable because if you see the plot of energy versus density of state dn, then it will look like this, right? Root over. So as energy increases, the density of states also increases, right? So that's a 4.3, and there it was 2.1. Okay, so next problem. So the mobilities for electrons and holes in pure germanium and also the pure silicons are given. Now we need to find the ratio of intrinsic resistivity for both the material. So anyone, what will be the answer for ratio of resistivity? That's the inverse of conductivity. Okay, so sigma is given as E into n into mu n plus mu p. Now let's say and okay, so then sigma germanium by sigma silicon will be uh, n germanium by n silicon mu n plus mu p for germanium, mu n plus mu p for silicon. Now here one information is missing, which is intrinsic concentration, right? So let me see what if there is any information in the question or in the previous question maybe. Okay, so yeah, it was given in previous question. So N for germanium is given by 2.5 into 10 to the power 19 per meter cube, and N for silicon is given as 1.5 10 to the power 16 per meter cube. So then if we find this 0.38 plus 0.18 by 5185. So the resistivity relation or the resistivity ratio will be just the inverse 1 by 5185, which will be around 1.93 into 10 to the power minus 4. So this is the ratio. So next problem, so there are two problems. 1.1 into 10 to the power 25. So lead has atomic weight of 207.2 in atomic mass unit, and then density of 11.35 gram per semi-cube. So the first question is number of atoms per semi-cube for lead we need to find, and then there is energy of vacancy formation in lead is 0.55 ev per atom. So let's say we want to remove an atom one by one from the whole lead sample. So then we need to give 0.55 ev energy per atom. So the question is number of vacancies per semi-cube at 500 Kelvin will be what? So let's try. So at least this question is very easy. Just so let's try to find the first question. So we are given density is 11.35 gram per semi-cube, and atomic mass M is 207.2 atomic mass unit. So, and we need to find the number of atoms per volume, per unit volume, right? So let's find first the volume. So mass by density. So volume will be, okay, so let's keep it there. Finally, we need to number of atoms. So there are Avogadro number equal to 6.022 into 10 to the power 23 atoms present in 207.2 AMU of mass, right? So then number of atoms per semi-cube will be, this 207.2. So Avogadro number basically Na into that atomic mass, density basically. Na into rho by atomic mass. So this is the number of atoms, right? So this will be, if we found the value, then it will be around 3.3 into 10 to the power 22 atom per semi-cube. So yeah, so basically the formula is Na by V, and here V will be that in regard to the atomic mass m. So number of atoms per semi-cube is this. Now finally part B will be, so 3.3 into 10 to the power 22. Now if the energy of vacancy formation in lead is 0.55 eV, so and the energy of vacancy formation, so equal to 0.55 eV per atom, right? And so number of vacancy per semi-cube is given by the formula n equal to, so here, so we know the n 3.3 into 10 to the power 22 atom per semi-cube, and then energy will be, this is energy for vacancy formation, 0.55 into by kBt, so 1.38 into 10 to the power minus 23 into temperature is 500 Kelvin. 16 vacancies per semi-cube. Okay, so this is the final answer, 9.57 into 10 to the power 16. Okay, now D. And this number of vacancies per semi-cube, this formula is nothing but just the Boltzmann distribution function. Okay, so it's a, in according to Boltzmann distribution, this is the concentration is proportional to minus energy by kBt. Okay, so according to this formula, we have this number of vacancies or the concentration of vacancies equal to the initial number of atoms and multiplied by the factor. Okay. Okay, so this was the last problem for today's session. In the next session, I will solve few problems on the thermal properties of uh, metals, and then maybe few initial problems on magnetic properties of materials. So thank you for joining. So I'm ending the session.